Hello, Mr. Mailer here, online math teacher, and welcome to my channel. Today we're going to be continuing my video series on trigonometry, and in particular we're going to be proving the double angle identities. So if you find this video helpful, consider subscribing and hitting the like button, and let's go. Now, I don't know what type of student you are, but when I was a student, and to this day, I've always been horrible at memorizing things. So what I'm going to show you is within proving the double angle identities is how we can leverage the addition and subtraction identities as well as a Pythagorean identity or two, to be able to recreate them fairly easily so you're not memorizing two sets. So if you know your addition and subtraction well, you can easily recover them. So the first one we're going to look at is the double angle identity for sine. And how we're going to use that is we are going to use the addition formula for sine. So I have my addition formula for sine right here on the right. So sine of x plus y is equal to sine of x times cosine y plus sine of y times cosine of x. And what I'm going to do is I'm going to be clever. I'm going to take from my left-hand side here my sine of 2 theta and realize 2 theta is the same thing as theta plus theta. So I'm going to think of this as sine of theta plus theta. Well, even though theta is the same thing, I can still apply my addition formula where I'm just letting both x and y be equal to theta. So when I do that, I get sine theta times cosine theta plus sine theta times cosine theta. Well, those are both the same, so the terms can add to leave us with 2 sine of theta cosine theta, which is equal to that right-hand side of the equation that we wanted it to be equal to. So we are done. So we have proved the double angle formula for sine. And it was just a quick application of this addition formula. So if you know this addition formula, you can easily recover the double angle identity for sine. Now, we're going to do the same thing next with cosine. So now cosine, if you remember the double angle formula, there's going to be 3. So we're going to start off with the easiest one, and that's the one where I just apply the addition formula for cosine in the same way I did for sine. So my addition formula for cosine right here, cosine of x plus y is cosine x times cosine y minus sine x times sine y. Now I'm going to again start with my left-hand side of my equation here, so that cosine of 2 theta, and I'm going to apply the same trick where I break 2 theta up and express it as theta plus theta. So I have my cosine of theta plus theta, and I'm just going to apply my addition formula for cosine to this, letting x and y both be theta. And when I do that, I obtain cosine theta times cosine theta minus sine of theta times sine of theta, and that's exactly cosine squared theta minus sine squared theta. So that right-hand side of the equation, we were looking to show it's equal to. So just, again, another direct application of an addition formula gives me my double angle identity for cosine. Now, to get the 2 other double angle identities for cosine, all you need to remember is that once you have this first one that comes from the addition formula, it's just rewriting the equation by substituting in for cosine squared of theta or sine squared of theta with a rearranged version of our favorite Pythagorean identity. So if I want to take cosine squared theta minus sine squared theta and change it with our favorite Pythagorean identity over here on the left, so sine squared theta plus cosine squared theta is equal to 1, I'm going to rearrange and solve for either cosine squared of theta or sine squared theta. So the first one I'll do is I'll rearrange and solve for sine squared of theta. And when I do that, I get sine squared of theta is equal to 1 minus cosine squared theta. And replacing sine squared in my first double angle identity will give me cosine squared theta minus, and all in parentheses, 1 minus cosine squared theta, which just simplifies to give me 2 cosine squared theta minus 1. So this is one of the other double angle identities for cosine squared theta. To find the third one, instead of solving for sine squared of theta, with my Pythagorean identity, I'll rearrange and solve for cosine squared theta. So I have cosine squared theta is equal to 1 minus sine squared theta. And now I'll take my double angle identity I got from the addition and subtraction formulas and replace cosine squared theta with 1 minus sine squared theta. So I have 1 minus sine squared theta minus sine squared theta, which is just 1 minus 2 sine squared theta. So we have our 3 double angle identities for cosine. One is just an easy, quick application of the addition formula for cosine. And then the other 2 come from direct applications of the Pythagorean identity, sine squared theta plus cosine squared theta is 1. So this is an easy argument to recreate any 3 of these if you need to. The final double angle identity I talk about is that for tangent. And again, it's just going to be a direct application of our addition formula for tangent. And the addition formula for tangent said tangent of x plus y was equal to tangent of x plus tangent of y, all divided by 1 minus tangent x times tangent y. So I do the same trick from before. Start with my left-hand side, that tangent of 2 theta, and treat 2 theta as just theta plus theta. And I can directly apply the addition formula by treating theta as both x and y to give me tangent theta plus tangent theta, all divided by 1 minus tangent theta times tangent theta, which simplifies to 2 tangent of theta, all divided by 1 minus tangent squared theta, which is that right-hand side from above that we want to show. So this is how I go about proving these double angle identities. So if you know your addition formulas really well, it's just quick applications of them to recover almost all your double angle identities, throw in a Pythagorean identity here and there. So I hope you found this video helpful. If you did, hit the like button and have an awesome day.